All right, let's work on a binomial distribution problem. So I have an unfair six-sided die. And so if it was fair, then each side of the six sides would have 1/6 of the probability, right? It would be a uniform probability distribution. But here it's unfair, and this sentence defines the unfairness. It is 4 times as likely to roll a 4 than any other number. Right, so that says that the probability of a 4 is 4 times the probability of any other number, right? I could be 1, 2, 3, obviously not 4, right? It can't be 4 times itself, but I could be 1, 2, 3, 5, or 6. So I can use this to find the probability. So the first thing that we're charged with is give the probability distribution of one roll of the die. So you're going to roll this six-sided die once. What are all the different events that are possible? Well, you could have a 1, you could have a 2, a 3, a 4, a 5, or a 6, right? You're rolling it once, and those are the 6 different options. So what are the probabilities of these events? So it's unfair, so we have to use this. All right, so if I have probability 1 plus probability 2 plus probability 3 all the way up to all of my events, probability 6, I should get a 1, right? That the sum of the area underneath the probability distribution is always going to be 100% if you account for all of your options, right? Because this is a six-sided die, I've got 6 things there. I know that when I add their probabilities together, I should get a 1. So let's let the probabilities of all the other things that aren't a 4 be represented by a dot. So that's a 1. That's the probability of a 2, right? They're the same. That's the probability of a 3. They're the same so far. Now the probability of a 4 is 4 times everything so far. So 1, 2, 3, 4. Right? The 4 takes up 4 times as much space as the 3, or the 2, or the 1. All right, so 1 plus 2 plus 3 plus 4 plus the 5 plus the 6 should give me a 1. So how many dots total do I have? I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. I've got 9 dots. So 9 dots is equal to 1. Each dot takes up 1/9 of a space. Right, so the probability of a 1 is a 1/9. In fact, let's go ahead and write our distribution down. If these are the events possible from one roll, and these are the probabilities of those events, then the 1 occurs 1/9 of the time on average. The 2 occurs 1/9 of the time. The 3 occurs 1/9 of the time. Now the 4 is 4 times as much as any of those. Right, those are the 4 dots over here. The 5 is a probability 1/9, and the 6 is a probability 1/9. And if we've done our job right, this should all sum to 1. And I do get 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9/9. I do account for all of my probability. So this is the distribution, or the probability distribution, for the events from one roll of the die. Now we're also charged with the second task. I need to give the probability distribution for the number of 4s out of 5 rolls. So I'm rolling this six-sided die 5 times, and I'm counting the number of 4s that can happen. So the number of 4s from 5 rolls. Right, so here I'm not really concerned with, am I going to roll a 6 or a 3 or a 2 or whatever? I'm just counting the number of 4s that I get out of these 5 rolls. So I could roll it 5 times and get 0 4s. And that's the event that's possible because I'm counting the number of 4s. The first event is I could have 0 4s. If I'm rolling it 5 times, maybe one of those 5 is a 4, maybe 2 of them, maybe 3 of them, 4 of them, or 5 of them, right? All 5 of the rolls could be the 4. And those are all my events possible, right? I can't roll 2.5 4s on a 5-sided die, right? And I can't roll a 4 9 times on a 5-sided die. So these are the events. Now we need to give ourselves the probabilities. And we will recover the probabilities using the binomial distribution. So recall what the binomial distribution is. By meaning two, right? There's two options. And that's exactly what I have in this scenario, right? I'm counting the number of fours. So you either roll a four or you don't roll a four, right? And the binomial distribution gives me the probability of rolling a certain number of fours. And that's exactly what I have here, right? What's the probability of me rolling 0 fours or 1 4 or 2 fours, right? So I can use the binomial for each one of these probabilities. So recall what the binomial probability distribution is equal to. If you have n attempts, P is the probability of a success. Right here, we're defining success as rolling a 4. And you're looking for, let's say we're looking for X successes. And let's let S be the number of successes. So the probability of successes equaling X, right? The probability of having a certain number of successes is given to us by n choose X, right? Because I want X successes times the probability of a success occurring X times and the probability of failure. So it's binomial. So there's two options. So if that's P, then the probability of not P is just the complement. Right, so n choose X, success happening X times, and failure happening the rest of the times. So n minus X. All right, so now we just have to write out the equations. So let's look at 0. What is the probability of rolling this 6-sided die 5 times and not getting a single 4? So that will be 5 choose 0. The probability of rolling a 4 was 4/9. You want it to occur 0 times. And you want the probability of failure. So the probability of not rolling a 4 was the rest of the probability, 5/9. Right? If you add up the 1, 2, 3, skip the 4, hit the 5, the 6. And how many times do you want to not roll a 4 if you're looking for 0 4s? You want all 5 of them, right? 5 minus 0. All right, so if we solve that, that's going to give us the probability. But before we do that, in fact, let's go ahead and do that. So 5 choose 0. So remember the choose equation. The number of ways that 0 4s can happen out of 5 rolls. So that's 5 factorial over 5 minus 0 factorial, also over 5 factorial. Right. Now, 4/9 to the 0, anything to the 0 is just a 1. And now I have this failure occurring 5 times. So 5/9 to the 5th. All right, let's work on 1 now. In fact, let me move everything over. Okay, now let's focus on this part here, the number of ways to choose 5 from 0. So I've got 5 factorial on top. 5 minus 0 in that parentheses just gives me 5. Oh, I'm sorry. That right there should be a 0. Right? Because in our choose equation, we ignore the number of ways to arrange the objects that we choose, and we're choosing 0 of them to be 4s. So now this should give us what we're looking for. I've got 5 factorial on top, and 5 minus 0 factorial just gives me another 5 factorial. That 0 factorial is defined to be 1, so I just get one way to do that. And that makes sense. You've got 5 rolls in front of you, and 0 of them are 4s. Well, there's only one way that can happen, right? All of them are not 4s. So here we get really just 5/9 to the 5th, right? A failure and then a failure, and then a failure, right? 5 times. So now let's do this for all of them. If I'm looking for the probability of exactly one of the rolls being a 4, that is 5 choose 1, a 4 happening once, a not 4 happening the other 4 times. So 5 choose 1 is 5 factorial over 5 minus 1 factorial, also over 1 factorial. I've got the 4 ninths happening once. I've got the 5 ninths happening 4 times. So this 5 factorial over 5 minus 1 factorial, 1 factorial. 5 minus 1 factorial is a 4. So what do we get here? This is 5, 4, 3, 2, 1. And then 4 factorial is 4, 3, 2, 1. And then 1 factorial is just 1 times itself, so 1. So I see a lot of cancellation. And I'm really just left with that 5. So this will be 5 times 4 ninths times 5 ninths to the 4th. Right, and that also makes sense to me because you're rolling 5 times and you're looking for the number of ways that 1 4 could happen. It could be in the first spot, the second, the third, the fourth, the fifth. Right. First roll, second, third, fourth, fifth roll. So the 4 could go there, or there, or there, or there, or there, right? Those are the number of ways that you can have exactly 1, and there's 5 ways that can happen. All right, and let's skip a little work here. For 2, it would be 5 choose 2, a 4 happening twice, a not 4 happening the other 3 times. For 3, it would be 5 choose 3. You want the 4 happening 3 times now. The not 4 happening twice. For 4, it would be 5 choose 4, a 4 happening 4 times, a not 4 happening the other time. And for all 5 of them, that's 5 choose 5. 4 ninths is happening all 5 times, and not a 4 happening no times. So if you do this and chase these equations down, 0, 1, 2, 3, 4, 5. So this is the distribution for the number of 4s in 5 rolls. So we should get roughly 0.053, 0.211. Let's say that that's going to be a 2. Let's round to 3. All right. For 2, that is a 0.339. 3, the probability of rolling 3 4s out of 5 rolls is 0.271. I have 0.108 for 4 4s, and the probability that all 5 of the rolls will be a 4 occurs 0.017% of the time. Okay, and you can check yourself, make sure that all of these sum to 1, which they should, because this is a probability distribution.